Welcome back. It's my pleasure to introduce our plenary speaker, Professor Marco Andreatta from University of Trento, Italy. And Professor Andreatta will talk about Gino, Fano, and modern projective geometry. So let's welcome him.
Okay, thank you very much. I'm very honored, pleased to be here to give a talk at this beautiful conference, a very big and important conference. I'm honored to do this. And well, I prepared a slightly general talk, not too technical, I hope. I hope it don't bother you too much. Of course, it will be a sort of appendix or, I mean, a subpart of the beautiful conference of Professor Mori. So you will find a lot of things, not at the same level, but and the idea was, since I come from Italy, is to stress a bit the figure of Gino Fano, which is an important mathematician, which was living in Italy at the beginning of last century, and which is nominated many, many times. Even the previous talk, we heard the name of Fano many times. So, projective geometry, we in Italy, we say that it was invented during the Renaissance period by these three guys, Filippo Brunelleschi, Leon Battista Alberti, and Piero della Francesca. And Leon Battista Alberti and Piero della Francesca, they wrote the first two books in projective geometry. They are two wonderful books. Here you can see a picture of it is not known if it is done by Leon Battista Alberti or Piero della Francesca. It is, I mean, they discuss who would be the, and this is a very nice example of projective plane. So the affine plane plus the line at infinity. The two guys, they wrote the first two books, very nice book actually, and recently I read the one of Leon Battista Alberti, and there is a beautiful introduction of projective plane, incredible, very nice. However, projective geometry was existence also in China, and this is a beautiful painting which is in the National Gallery here in Beijing. I hope to see it on Saturday, and this is attributed, I cannot, the painter is Gu Wongzong, and the night reveals of, well, it's the description of some night events, and they are really depicted, painted in projective, in perspective style. So also in China, we have this much earlier actually. But the previous person, they really wrote books, they wrote a theory about projective geometry. Okay, starting from this artistic point of view, we mentioned what is the problem of projective geometry to classify projective variety or algebraic variety contained in projective space. They are algebraic. So there is a famous Riemann-Poincaré theorem. We say that in dimension one, there are three types of curves. The Gauss sphere, elliptic curve, Abel and Jacobi, and the hyperbolic disk, mod the fundamental group. And it depends if you are in Italy, you say it is a Beltrami disk. If you are in German, you say Klein disk. If you are in France, you say Poincaré disk. And it is attributed to all of three. And so the difference is that Gauss sphere has an Hermitian metric with positive constant curvature. The other is zero, and the third one is negatively curved. So this is a classification, as was told by Professor Mori, according to the positivity of the tangent bundle. And as we have known, I mean, to extend these things in higher dimension seems not to have much reason, because if you have, well, except, I mean, this is a very beautiful theorem proved by Professor Mori in 1979 and later in the complex case by Xiu and Yao. And if the tangent bundle is ample, let's say that, then it has to be Pn. So you see, I mean, if you want to stand it in higher dimension, positivity of the ampleness of line bundle will give just one example, too few. And let me add this beautiful theorem, as, which is a Frankel-Archer conjecture, as a sequel, of which I am very proud. Beside a Frankel-Archer conjecture, we can have Campana-Ternère conjecture. We say that you do not need the tangent sheaf is ample, but you just need that you have an ample subbundle sheaf. So this is a sort of generalization of Frankel-Archer conjecture or proof. And of course, it is strongly based on Maury's result. It's an extension of his proof. And we got it with Wisniewski some years ago. Okay, so this is too strong. So a more relaxed assumption should be to have the positivity of the determinant of the tangent bundle, not of the tangent bundle, but of the determinant. And if you have the positivity of the determinant of the tangent bundle, then you have a so-called Fano variety. Minus kx is called is the determinant of the tangent bundle, and the positivity, the ampleness of minus kx is. Actually, Fano did not give this definition, but he studied varietà algebrica a tre dimensioni a curve sezioni canoniche. So he was studying threefold, such that for general hyperplanes, the two general hyperplane sections, the curve is canonically embedded. So he first studied this kind of threefold, and he proved that for all these threefold, you have all numerical invariants are zero, like for the projective space, okay? He proved that this is the case if and only if minus kx is actually very ample, and it embeds the threefold into a projective space of dimension g plus 1 of degree 2g minus 2, where g is the genus of the general hyperplane curve. So, I mean, for him, Fano variety Fano threefold was something for which minus kx is very ample, okay? Nowadays we say simple. More generally, actually, Fano considered projective n-fold. So, Fano was probably the best Italian geometer who went out of surfaces and went on higher dimension variety, on threefold and fourfold, and he studied n-dimensional variety for which the general hyperplane curve is canonically embedded. And he proved that this is the case if and only if minus canonical is divided by n minus 2 times the hyperplane section. We say today that Fano variety of index n minus 2. Okay, the very nice things of Fano variety is that up to a certain dimension, they can be classified. And this is very nice, because this was a game which was done by a lot of persons last century with a lot of success. Well, in the case n equal 1, we have seen Riemann Poincaré, they say that it is only P1. In the case n equal 2, it's the famous Del Pezzo surfaces, again in Italian. And in the dimension 3, there was this beautiful, many beautiful papers by Fano himself, by Skoski, by Shokurov, by Mukai, by Mori, and there is a complete classification of Fano threefold, smooth Fano threefold up to now, okay? Well, let me say, I will talk a little bit in the while. If you see, Skoski claimed, and he was partially right, that Fano missed the x22, degree 22 in P13, but actually, he constructed it, and we realized we found a paper in the Conti dell'Accademia di Lincei of Fano, of which I will talk at the end of the talk, in which he actually constructed it. Unfortunately, the construction of Fano gave a Fano threefold at x22 in +13, which is not prime. And it is among the Mukai-Mori classification. So it was not forgotten by Fano, let me say that. Okay, I mean, nowadays you can Google and you can find a site called Fanography, a tool to visually study the geography of Fano. So there is a lot of nice video, an app to a nice application to study Fano nowadays. The classification of Fano's variety of dimension 3 and 4 with terminal singularity is a long-standing and ongoing project. I like to mention Alessio Corti, but many others, the Russian school, English and American, the Japanese and Chinese. There are a lot of people working on this. We have also seen positive characteristics the previous talk. Let me mention that Mukai classified all Fano variety of dimension n-2, of index, sorry, n-2, which were the original Fano's examples, definition. He classified it under the assumption of the existence of a good section in the hyperplane section. And the assumption was then proved by a student of mine, Massimiliano Mella. So the classification of index n-2 in every dimension is done, has been done. Okay, so they are nice. They are a very nice object. And of course, let me mention some very well-known problems and results obtained last centuries connected to Fano threefold. This was the goal, actually, of Fano, to prove that this variety, which has all the numerical invariance 0, some of them are non-rational. There are no satisfactory proof of Fano of this fact, so he was probably not able to give a good proof of, I mean, it is not considered to have proved it, but there are proofs of Clemens, Griffith, Iskowski, Manning, Artin, Mumford, very known, very nice result. Another beautiful quality of Fano manifolds that they are covered by rational curve. And this is, as it was said in Mori talk and also by other speakers, this is one of the most wonderful results in projective algebraic geometry, which actually deserve a proof probably also in the complex case, but the existence of rational curves. This is a splendid idea of Mori and the proof. And they are actually rationally chain connected. The set of Fano varieties of fixed dimension form a bounded family. This is a result of Koller, Miyaoka, Mori, and independently by Nadel, and in the singular case by Birkar, let's say. So very nice results, which say that you can classify them. They are bounded, right? This is very nice. And the last things, which I should mention, well, Fano is really, he found a very beautiful idea, and the only one which could not admit a Kelenaist Einstein metric. And they have it if and only if they are k-stable. A lot of people are studying this kind of problem, among them Donaldson, we proved it. Okay, so on one side we have Fano manifold, which are very important, very nice to study, and in some sense also, I think that the approach of Fano was exactly the correct, the modern one. I mean, to slice to a curve and to lift the results of canonical curves to the threefold. And opposite to Fano, we can say that something is, so we take a projective variety with mild singularity. We can define a power of the canonical bundle as a line bundle, and we say that it is Neff if restricted to every curve is bigger or equal than 0. And this is the definition of Neff, which is very well known nowadays in algebraic geometry. And if you have a variety of this type, it is called the minimal model. And you know that we have a very nice conjecture. If X is minimal model, then a power of the canonical bundle has to be generated. And so it is semi-ample. So on a minimal model, you have a very nice instrument. You have the pluricanonical map, and you can study the variety via this map. So, but if abundance conjecture is true. The Morris idea, inspired by Castelnuovo, Enriquez, and Fano, is that a projective variety with mild singularity either as canonical, as Kodaira dimension equal to minus infinity, I don't know why, well, this is equal, okay? So conjecturally it is uniruled, or X is birational to a minimal model. So either it has Kodaira dimension minus infinity, or it is birational to a minimal model. This has been organized in a program, as we were told during the lecture of Professor Mori, which has been successfully developed in the last 40 years. But we still have many open questions, and as all mathematical programs, they develop and you increase and increase its properties. Let's say that Birkar-Caccini-Ekman-McKernan theorem is the best result of the moment on the existence of minimal model program in many cases. What is it? What is more? I mean, really roughly saying what is a minimal model program. Summarizing Mori theory, I hope I'm correct. We said that a curve for which kx is negative, if you have a curve on which the canonical bundle is negative, then the cone of effective curve is non-empty, and it is probably the part of curve for which the part on which the canonical bundle is negative is a polyhedral cone generated by rational curve. This is the famous cone theorem, and you can contract these bad curves. Let's call it bad, okay? Curves on which the canonical is negative. So, in order to reach a minimal model, you take a curve on which the canonical is negative, and you contract it, okay? Very simple, but very difficult to do. And the cone theorem, the description of the negative part has been done by Mori and other people, Mori in the threefold case, and the existence of a contraction, the fact that you can contract the negative part is a theorem by Mori in the smooth case threefold, Kawamata, Shokurov, and I'd like to say, Fano again, if you have a contraction of an extreme array, the fiber will be Fano variety, and we call it Fano-Mori contraction. So these are the fundamental map in the minimal model program. I think it's clear, right? So you want to get an F canonical bundle via birational map. So if you have something negative, you contract it, okay? And minimal model program proceed inductively with two steps. You contract, and you get a new variety if it is birational, and if it is birational and divisorial, sorry. If it is birational but not divisorial, then you make a flip. I do not want to say what is a flip, but I will say in a while. It's a very delicate procedure, I think, well, introduced by Mori, but I mean, it was on the air in the 80s. I think there was a beautiful example. Let me stress the Italian style by Paolo Francia, an Italian mathematician, who gave a very nice example of birational contraction, a Fano-Mori contraction on a threefold, which is small, which is not divisorial, and he was able to flip it. Okay. Of course, I mean, in order to have a minimal model, we know that we have the ray, we know that we have the map contracting the ray, and we have to know the flip. Because, I mean, it's easy to say, okay, if you have a small contraction, just flip it, but you have to do it. This was the problem. So you really have to study the structure of this contraction and understand. To take a minimal model happen, one need to classify Fano-Mori contraction. Okay, here are some results on the smooth case. As it was said, in the surface case, we all have only one type of birational Fano-Mori contraction. This is the famous Castelnuovo contraction theorem. On the surface, you just blow down a -1 curve, okay? So this is simple. So you start with the surface, and you want to reach a minimal model, you contract -1 curve. Easy. Then there was this beautiful theorem of Mori in 1981. In dimension 3, if you have a smooth, let me stress a smooth, threefold, then there are 4 types of contraction. A blow up of a smooth point, blow up of a smooth curve, blow down of divisor to a smooth curve, blow down of divisor to a smooth point, or you can blow down a divisor which is isomorphic to P2 with normal bundle -2, or a quadric with singular or smooth into a singular point. Okay, so I consider this a very beautiful theorem, and it is really constructed. I mean, you can see Mori constructed, I mean, in the spirit of Fano. So you have this extremal contraction on a smooth threefold. There are 4 types of them. These are. So we like this theorem so much. And with Jarek in 1998, we did it in the 4-dimensional case. So in the smooth case, smooth, 4-fold, all Fano-Mori contractions of divisorial type are, well, I didn't put the list, but you can go on my paper, on our paper, and see. There is a one type of small contraction, which was constructed by Kawamata. In the smooth case, there are no small contraction on threefold. They appear in the singular case. And so there is a complete description of Fano-Mori contraction in dimension 4, which are birational. And let me say that the nice thing in this case is that you have blow up with jumping fibers. So you can blow up a divisor, sorry, a surface, and you have usually one-dimensional fiber, and so you can have some two-dimensional fiber inside. Very nice example. We liked it very much. We spent 2 years or more to have this classification, working on Mori's instruction given in. Okay. Of course, it was very clear at the very beginning that the smooth case is not sufficient. You enter into the singular case, and there was this monumental paper by Mori in 1991, and then of Collar-Moore in 19, classified all small contraction on threefold with terminal singularity. Let me say, starting from, and inside this big list, you can find also Paolo Francia example, and Mori classified all small contractions, and he gave also a flip for every contraction. Okay, yesterday, 2 days ago, in his talk, he spoke about cubism. Let me say that when I look at this paper, frankly, I didn't read all these papers, but it seems to me like they are artists of these glass windows. This is in Paris. And so, I mean, every small part is a small contraction with its flip, okay? So it's a monumental, it's really an artistic hard work made of a huge picture of all possible flip, small contraction and flip. So let me say something. Together with the termination of flips, which was done by Shokurov, this gave minimal model program in dimension 3. So this is the as Professor Mori was saying, he's still working on classifying all birational divisorial contraction on threefold with terminal singularity. So besides flips, we have contraction of divisor to a point or divisor to a curve. And there are a lot of papers by Mori, Prokhorov, Kawakita, and many others actually. Kawakita, they were the first one to study the case of divisorial to point. I think that more in Prokhorov, they were working on divisor to point. So I like very much the things. I mean, we know that minimal model program works for threefold, but in this way we have all the possible instruments of minimal model. So we classify everything. The classification of Fano-Mori contraction of fiber type included Fano variety. On terminal variety of dimension 3 is a long-lasting job which is carried on by many groups all over the world. So the case of threefold fiber type. Of course, sorry, yeah, it was clear, right? A minimal model program takes you to a minimal model or to a Mori fiber type contraction, to a Mori fiber type contraction. Kocher-Birkant recently stated that under some additional assumptions, they form a set of bounded families, and so they, in principle, they could be classified. They are fine. Okay, let me recall another theory which is strictly connected to Fano's result. And this was the way of doing of Fano, take a projective variety with a polarization. So you take the hyperplane section, okay? And it makes sense. Somese and his school, I actually started to work in algebraic geometry in 1985. I spent 1 year in the United States. And then Somese asked me, do you know this paper of Fano and Mori? And Morin, sorry, not Mori. And I said, no, I didn't know anything actually. I even didn't know what algebraic geometry was, some sense. So I started to study. And it was explained what is the so-called adjunction theory. So even in surface case, Enriquez and Castelnuovo, they developed the classification of surfaces independently on the polarization, but they wrote also some paper related to a polarization. So they took an hyperplane section and they studied the adjunction bundle, which means Kx plus H. You make a junction. you take an hyperplane and you add it to kx. And according to the positivity of the junction bundle, you can classify the surface, or in the case of threefold, Fano considers the case kx plus 3h plus 2h and plus 1h. So in the case of threefold, I mean, R goes from the dimension up to 0, up to 1, say, and according to this sort of process, let me see. So, well, maybe I'm too vague. Let me say it again. You take a projective variety, you take a hyperplane section, and you study the positivity, actually the netness of the junction bundle. The theory is settled if well, you take a rational number is bigger or equal than n minus 2, and recently I'm considered the case R bigger or equal n minus 3, which will be a very vast case. And so let's put the case n minus 3, and this is done by lifting the classification from the three-dimensional case, in particular lifting the structure of weighted projective blow-up. So let me say, a junction theory works because it is able to lift the classification of surfaces, in the case R equal n minus 2, to higher dimension. You can lift the case of threefold in the case n minus 3. And so it is a very nice instrument to have. I mean, minimum model programming is much stronger, but a junction theory can help you in giving classification, explicit description of examples of special cases, okay? And let me say that I was studying the case n minus 3, as I said recently, 2 or 3 years ago, and I was trying to lift things from threefold to n-fold, and I didn't know how to do. And then I ran through the first paper, I think, of Mori, lifting weighted projective space. I think it's your first paper, is it? So very, very long ago, probably very simple for you, but I liked it very much, and I applied it in the relative case, okay? So you were doing it in the projective case, and I did it in the relative case. And so I was able to, now I can extend all the results on threefold, classifying small contraction, creep, and, divisorial contraction to higher dimension via the assumption of a junction theory, okay? So very nice, very nice. Let me say that this is a very nice way of producing example. Okay, in order to summarize what, I mean, the purpose of this talk is that Fano was very important in developing a lot of mathematics. His ideas, or at least his name, was in the back. Well, we celebrated many times in this conference, but he got a field medal because he was working on Fano manifolds, and he got this prize yesterday. And Hakon and McKernan, they got the breakthrough prize, and Birkar got a Fields medal. And this is the only place where it is written Fano, but I think it should be written also in both of them also. And Birkar got also the Frontier of Science Award. I think that part of their work, and consequently of mine, is based on Fano. Okay, I think I went too fast, but I just wanted to to mention how many beautiful results are connected to Fano, or at least to his name. And the last part of my talk, which is more technical, I would like to tell you about a funny story. This is Fano. This is Fano, which was living in 1971, 1952. And in 1959, so he was almost more than 70, right? Yeah, 73, I think, if mathematics. So 3 years before dying, he wrote this beautiful paper in which he say, okay, I forgot up to now to construct a threefold of degree 13 in P20, well, I don't remember, this one, and I want to construct it. This is published in Accademia dei Lincei. It is written in Italian. The funny thing is that it came out 1 year after the publication of Roth's book in English. Roth's book in English was summarizing all results of Fano, and so this book, this paper was not included. And this is why I think that many people, Mani, Niskoski, probably they didn't read it, maybe. And it is, I don't know, it is really 4 pages, very short, incredibly hard to understand, to me at least. It took a lot. Fortunately, I was helped by Roberto Pignatelli, and in this paper, he constructed a threefold of type degree 22 in P13 with canonical curve section. Okay, so we started to read it, and we understood that Fano considered a smooth, rational, quartic normal scroll embedded in P5, so a surface, rational, quartic surface in P5 of degree 4. This is the one. And then he defined M4 as the subset of the Grassmannian of lines in P5 given by the chords of S22. So he considered all the secant and tangent lines to the smooth, rational quartic surface, a normal scroll. So he considered a special surface, and he considered all the secant and tangent lines. And he embedded this in the Plucker embedding, okay? This is M4. This is a variety of dimension 4 embedded in P14. Pay attention, this is not the Fano threefold, this is a fourfold. As an irreducible, he proved that it is as an irreducible smooth variety of dimension 4, that it has degree 22, and that the sectional genus, so if you take 3 hyperplane sections, you got a curve, and whose genus is 12. So exactly something which he was searching. The funny thing that he didn't prove smoothness, he gave it for free, and this is strange. It is smooth, it is smooth. We were able to prove that it is smooth, but how he knew it, we do not know. That it has dimension 4 is not difficult. Then he proved that it has degree 22 in a wonderful way. Wonderful, and we copied it. It took 2 months to understand his proof, of maybe less, but I don't know. I mean, when we met, we were working on this. And then he proved that the sectional genus is 12. The difficult thing was to prove that the degree is 22. And we liked it very much, so we published a paper on this on Rendiconti dell'Accademia dei Lincei. Subsequently, having a fourfold of degree 22 with sectional genus 12, he took a hyperplane section, and this would be a threefold of degree 22 with a sectional genus 12. So it will be a Fano threefold. So this is a Fano fourfold in the sense of Mukai, say, and this is so this was his construction. Let me show it again. So it took this surface, it took secant and tangent lines, and the set of them was embedded into the Grassmannian, and it is a Fano variety. Very nice, very nice. To me, the unexpected thing is that it is smooth, and okay. This is a bit technical. Let me say some words. We try to generalize Fano construction in more general case, and so and in modern setup, okay? So in general, we take a Hilbert surface, and we take the Hilbert scheme of zero-dimensional subscheme. Hilbert scheme of length 2 points on the surface, okay? And they correspond to secant. The nice thing, you see, to prove smoothness and things like that, you need scheme theory, which was not available at Fano times. So this is really a bit strange how it was able to prove it, because he was then computing the degree cutting with hyperplane, but not with general hyperplanes, but with special hyperplanes. So he was really working as a modern algebraic geometer, cutting with hyperplanes, but without caring if the intersection was set theoretical or scheme theoretical. The problem is the scheme theoretical proof, which was very delicate. So we were able to provide all the details about schemes involved in his theorem. But on the other hand, at a certain point, we decided to change and to use, for instance, Hilbert scheme. And this is a very beautiful result by Fogarty, that the Hilbert scheme of points on a surface is a smooth variety. Moreover, there is a complete description of the Neff cone. It has 3 faces associated to elementary contraction. And so we have on this, okay, it's clear that Fano was interested in the case 0, F0. So P1 cross P1. But we can do it in general for every Hilbert surface. We consider it the Hilbert scheme of length 2, which is a smooth variety, and it has 3 types of contraction. The Hilbert to Chow contraction, the contraction of the divisor of all pairs of points on a fiber of phi to a smooth rational curve, and this type of contraction, so I'm talking the language of Hilbert scheme, and this type of contraction we can prove that it is smooth, and it is the blow-up of a smooth rational curve. And this follows from a result of myself and Gianluca Occhetta. So we know that this type of contraction is smooth, and then we have a third type of contraction, which contracts all pairs of points on the section at infinity to a singular, and this is a contraction to a singular point on the contrary. Okay, so this is a general description of this abstract space, the abstract space of Hilbert schemes on of length 2 on a Hilbert surface. Now, this is abstract. in order to make it concrete, we search for a projective realization, and we consider the smooth rational normal scroll. So we embedded this Easterbrook surface in PR plus 1 via this way. Again, the case of Fano was B minus A equals 0, and AB is 2 and 1. So Fano is one special case. And then we take the morphism. I think it is very natural, associated to a scheme of length 2 on the Hilbert surface. We associate the line passing through this Hilbert scheme through these 2 points in the Grassmannian. So this is a very general map from the Hilbert scheme to the Grassmannian. And we associate to each zero-dimensional 2 scheme the line passing through these 2 points, or point with a direction, okay? Very natural map. This is a modern, say, but not so modern, but they say actual way of describing Fano construction in all cases. We call it the secant maps, and its image AB. And, well, I mean, the first part was really very general. I don't want to enter too much into details, but let me say here are the 3 elementary contractions that I have on the Hilbert scheme of P1 cross P1, and they can be interpreted. They can be realized geometrically. Well, I'm not providing too many details, I'm sorry. So the map, let me say, X22, so it's the map given by the previous 2-2 map, is the Fano M4, and after we know by this result that this is a smooth blow-up of the curve, and we turn out that this is exactly example 2 in the classification of Mukai of Fano fourfold of index 2. So we described Fano construction via in this new language, and we found out that it is included in the example given by Mukai in the fourfold case. And let me say these things, that we were able, with Ciliberto and Pignatelli, to exploit the Fano computation of the degree in the general case. And we prove the degree of XAB, in general, we have a formula for the degree of the secant variety, which is a very nice formula. And when we got it, we immediately check it for R equal 4, for the case, and it agrees with Fano, at least. And it agrees also with the formula given by Cattaneo some years ago, but Cattaneo has stronger assumptions and also different type of surface sometimes, but he was assuming that the surface is embedded by a three ample divisor, so I mean a stronger assumption. So I think this is a very nice construction, and I will conclude with this. I say that there was this beautiful example of Fano, which he constructed this X22 in P13, which was neglected, and it is very original, taking secant line of surfaces, of a surface, we generalize it to other examples, and it turns out that we can compute in the Fano's way the degree of this new variety, which is a fourfold. They are fourfold, except for the only Fano one was the one of Fano. There are other ones which are Fano, but they are singular. They are singular, okay? And most of them, they are not Fano, but they could be nice for constructing other things. And yeah, this is a result on the okay, Fano, last Fano, according to Fano, is a general hyperplane section of this M4, and given this new description, we realize that an hyperplane section of this M4 is the number 16 in the Mori-Mukai list. So, of course, it was neglected, but it was described by the complete list of Fano variety, and one can show that this FLF stays for Fano last Fano is also an hyperplane section of X13, which is Fano but singular. Okay. The beautiful thing of this construction is that you can exploit birational geometry of this example. So there is a birational map from X22 to X13, which gives rise to a birational map between Fano threefold and things like that. So the geometry of this example is very nice. Probably not deep as the first part, but there are very nice construction. So I just want to stress that we enjoyed very much in the last 2 or 3 years ago finding that Fano is still interesting to read. Thank you very much.
Thank you very much for our enlightening talk. Any questions for the speaker?
There's a family of Fano threefolds of degree 22. Can you point out which one in the family he described? I mean, for instance, there is something, there are compactifications of C3.
I'm sorry.
I mean, there's a family of Fano threefolds. Yes. Can you identify which one was constructed by Fano? I mean, some with special properties.
I don't know. I don't. Well, I mean, this was the number 16 in the Mori-Mukai list, right? What do you mean by which is the one in the family? You mean?
Yeah.
Well, there are many because you can choose. Is the blow up of the conic in the intersection of Q4 with another quadric? They are all of this type, and so it depends which intersection you take. No, I am not able to answer it.
Okay, so we can discuss.
Yeah, sure.
Other questions?
Thank you very much for the very nice talk. I just want to make 2 corrections.
Sure. Yeah. Of course.
Yeah, you mentioned the Mori-Collar classification of flips, yes. Flipping contraction. There, we were working on analytic minimal model program. And so fiber is always irreducible curve. Yeah, so if it's reducible, there are many more cases. I'm still working on them. So
you cannot assume that it is irreducible? No.
Yes, I did. I could. If I go to analytic category.
Yes.
Yeah, so that's what I was doing. Yes. So to do the flip, we run analytic minimal model program.
Yes.
Yeah.
Yes. Yes. Yes.
That's what I'm saying.
Yes. Yes. That's a very delicate question. Yeah. Sorry. Yes.
The other one is this about the cone and extremely description. You said on the K negative side, it's locally polyhedral.
A little bit outside, you mean?
Yeah. But rigorously speaking, it's not polyhedral. If you consider a circle and a point, and if you span,
Yes?
it's if circle is the base, it cannot be polyhedral. So you could say locally finitely generated or something.
Okay.
That's what I'm saying.
Perfect. Thank you very much.
Other questions? If not, then let's thank the speaker again.